Hello, everybody. So we're working in Chapter 7. You've started the reading assignment for Chapter 7, which is excellent. You're noticing probably now that I'm giving you a video on 7-3. You're probably wondering where's 7-1, 7-2. Well, we're going to skip videos on those because multiplying, dividing, adding, subtracting, talking about decimals in general, I think it's definitely something that you can review on your own. These are all operations that we've learned in elementary school, so maybe we've forgotten how to do them, but it's not impossible for us to remember what we've already been taught about them. And a lot of it relates back to fractions. So we did all of those videos with the fraction worksheets, and hopefully that helped to build your understanding so that you can do decimals with them. The sections that I do think would be beneficial for you to have a video on are 7-3 and 7-4, so I'm going to focus our energy on that. Starting with 7-3, let's talk about repeating decimals. We've read about decimal numbers, and we know enough to know that decimals can be terminating, like 0.23456. That number stops. There's no digits following the 6, so we call that terminating. We know that terminating decimals come from fractions whose denominators only have factors of 2 and 5. For example, we could have 1 over 10. That turns into the terminating decimal 0.1. But we also know that not all decimal numbers terminate. So that's where we're going to focus non-terminating decimals. A non-terminating decimal can either have a pattern or not have a pattern. For example, I can think of a number like 0.3 repeating, where the 3 continues, it never stops. And maybe you remember there's another way to write that using the bar over the 3. But then there's also non-repeating decimals. These are decimals that continue, but they have no pattern. And I can try and make something up here. And it just never ends. And something that's tricky is that often we forget that our calculators are automatically rounding numbers for us. So if I do a division problem on my calculator, it might look like the decimal terminates because there's not the 3 little ellipses dots to the end of the number. But that's because our calculator has a limitation on it. It can only display so many digits, and at a certain point, it's going to round up for us or round down according to the last digit that it's able to calculate. So we have to keep that in mind. Just because your calculator stops showing numbers at the 2, for example, maybe your calculator can handle showing this number, that doesn't mean that there weren't other digits after it. So we have to be really careful with that. If you tried to calculate the division by hand, you might be able to find the remaining digits. But this section is not talking a bunch about non-repeating decimals. We are talking about repeating decimals. So we're focusing specifically on decimals that have a pattern, and there's a couple of language things that we need to clear up. So some definitions. First is that we're going to have a new word in our vocabulary called the repeatend. The repeatend is the string of digits that repeats. Our book calls it repeating block of digits. For example, maybe I'm looking at a number like 0.147, You can see that there's a pattern, and we can see that the pattern comes from the 3 digits 147 repeating. So this is our repeatend. Sometimes the repeatend doesn't always show up right after the decimal. We could have a number like 0.123147, These two decimals are both repeating decimals with the same repeat end, but it just appears in a different place. Another definition, let me scroll down here a little bit. Another definition that we need for this section is the period. The period is essentially just the number of digits in the repeat end. So in the example that I talked about with these two repeating decimals, our period, if I could spell period right, our period is 3 because the repeat end has the digits 1, 4, 7, that's 3 digits, so our period is 3. With repeating decimals, we can identify when they're going to happen basically by doing the long division. So let's do an example of that so I can show you where it pops up. Let's do 2 divided by 13. So this is coming from example 10 in the book. If you wanted to refer back to that, you can. 2 divided by 13, if we set that up using long division, it's 13 goes on the outside, 2 goes on the inside. Now we know that 13 doesn't fit into 2, so we add our decimal, copy it up into our quotient, and then add some zeros afterwards so that we can fit 13 into our number. And we're allowed to keep adding zeros until we're finished, right? So there's really no such thing as a remainder when we're dividing and allowing decimal answers. We used remainders when we were dividing and we only wanted whole number answers, but now we're going to represent that remainder as a decimal. So we'll start off with 13 going into 20. So we know that 13 only fits into 20 once. So 13 did not fit into 2, so we put a 0 above the 2. It fits into 20 once, and then we'll subtract our 13. That leaves behind 7. And then we bring down a 0 so that we can move on to the next place value. This time we're asking how many times does 13 go into 70? 13 goes into 70 5 times. 5 times 13 is 65, so we're going to subtract that. That leaves behind 5. We're going to need to add another 0 so that we can continue our division here. This next step, we're asking the question, how many times does 13 go into 50? 13 goes into 50 3 times. 3 times 13 is 39, so I subtract the 39. That leaves behind 11. I need to add another 0 here because I need to keep dividing until there's a 0 remainder, kind of like that Euclidean algorithm that we learned in a previous section. So, trying to keep my colors straight. This time we are asking how many times does 13 go into 110? It's going to go in a total of 8 times. 13 times 8 is 104. We do our subtraction there. It has 6 left over. Still not a 0 remainder, so we're going to add another 0. Bring it down. Now we're asking how many times does 13 go into 60? It goes in 4 times. 13 times 4 is 52. Subtract that, we have 8 left over. Still not a 0 remainder, so we're going to add another 0 and then bring it on down. We're asking now how many times does 13 go into 80? 13 is going to go into 86 times. 13 times 6 is 78. We do our subtraction and we have a 2 left over. That's still not a 0 remainder, so I would add another 0, bring it down, And now I'd be asking the question, how many times does 13 go into 20? But we already asked that question. So essentially what we're seeing here is like deja vu. We have already gone through this process. We know what happens. You start off with 13 going into 20, and then you have a 7 remainder, then you're looking at 70, and then you're going to go through all of these numbers again. The same exact thing is going to happen, which means we know that this string of digits in our quotient is going to repeat. So we know that 2 divided by 13, let me switch this back over to white. 2 divided by 13 is going to leave us with the decimal 153,846 repeating. That's our repeatend. So the full repeatend, 153,846, that's going to continue. In fact, if we tried to write it with the expansion, and then I could do 3 ellipses there if I wanted to. So when you're doing long division, if you recognize that you're in the same position that you started in, then you immediately can say, oh, well, I know that I'm going to get the same results. So what follows from here is going to repeat. All right, so that's, I feel like, a pretty decent introduction to repeating decimals. Next, we're going to take a look at how we would write a repeating decimal as a fraction. So we're going to start with a repeating decimal, and then we're going to transform it into a fraction, and that's essentially what this headline is saying here. And if you'd like, you can match this up with page 360 in your book. We're going to start off with the exact example that the book gives us. So 0.55 or 0.5 repeating. This is the decimal that we're starting with. So start with a repeating decimal. And then we're going to transform it into a fraction. To do that, the first thing we're going to say is, let's let x be a rational number, meaning it's of the form a over b. So we learned that in chapter 6, that rational numbers are fractions. They're a over b. And b, the denominator, is not allowed to be 0, just to be sure. So we're going to let x be some rational number, and I'm going to set my unknown rational number x equal to this repeating decimal, 0.5 repeating. And we're going to use this equation to create a second equation that allows us to solve a system. For example, I can multiply this equation by 10 on both sides. And that's going to change the equation to look like 10x equals 10 times 0.5 repeating. Well, remember that 0.5 repeating is this number. And if I multiply that by 10, it just moves my decimal over 1. So where the decimal used to be, it's going to move over 1 position to the right. So 0.5 repeating times 10 becomes 5.5 repeating. And this is perfect because I can use these two equations kind of against each other to eliminate the repeatend. What I mean by that is I'm going to kind of create like a system of equations with the 10x equals 5.5 repeating and the x equals 0.5 repeating. And I want to solve those two equations by adding them together. I'm sorry, subtracting, not adding. In other words, you're adding the opposite. So if I were to subtract the bottom equation from the top, on the left side that would look like 10x minus x. On the right side that would look like 5.5 repeating minus 0.5 repeating. And if you prefer, you can write that vertically. 10x minus x is equal to 5.5 repeating minus 0.5 repeating. I kind of like the vertical version because it's easy to see that the repeating portion of our decimal is going to subtract off. So this 5 repeating subtract this 5 repeating gives me a 0 to the right of my decimal. And then 5 minus 0 to the left of my decimal is just 5. So I get 5.0 on the right, no repeating decimal left at all. Then on the left, 10x minus x. Well, if I have 10 x's and I get rid of one of them, that just becomes 9x. So my new equation looks like 9x equals 5. And because 5.0 is no different than 5, I'm just going to write it as 9x equals 5. And I don't need the 0.0 anymore. And our goal was to find that x, the rational number, that's equal to our repeating decimal. So I will solve that little equation for x by dividing both sides by 9. That way on the left I just have x, and on the right I have 5 over 9. And you can double check this. Type it into your calculator. You will see 5 divided by 9 will give you a repeating decimal of 0.5 repeating. Now, be careful because in your calculator you might see something like 0.55555, lots of 5s, and then a 6. And that might tell you, it might make you think, oh, this is not repeating because that's 6 at the end. But be careful, that 6 at the end came from your calculator rounding. So in reality, doing this division, you would just continue to get 5, and then another 5, and then another 5. You'll never get a 6. So 5 divided by 9 is not equal to this calculator number. That's an approximation. So just to be clear, let's make sure that we address that. 5 divided by 9 is truly equal to the decimal repeating, 0.5 repeating, and it's fine to write that as 5 with the ellipses after if you want. What is not okay is writing 5.9 is equal to 0.55556. You know, no matter how many 5s I squeeze in here, this is not okay. Those things are not equal. In fact, it's just an approximation, so you could just say 5 divided by 9 is approximately 0.55556. That's fine. But if you want to use a real equal sign, then you need to indicate that the 5 is repeating. What we just saw is that any repeating decimal can be rewritten as a rational number. I'm going to show you a few more examples because each repeating decimal is going to have a slight different process for turning it into a rational number. And the process only changes because the repeatand is different, the period is different, and where the repeatand shows up. So let's try this decimal, 0.235 repeating, and it's the entire 235 repeatand that we have here. We want to write that as a rational number. So we start off by letting some rational number x be equal to our repeating decimal. And then we're going to multiply this equation by powers of 10 until we get an entire set of the repeatand to the left of our decimal. So in this case, if I did 0.235235 and I just multiplied it by 10, that would move my decimal once. That would look like 2.35235 repeating. So one factor of 10 isn't going to cut it. If I multiplied it by 10 twice, that's like multiplying by 100. That would move my decimal 2 times. That would look like 23.5235 repeating. We're getting closer. The entire repeat end has not appeared on the left yet. So let's try one more multiple of 10. So this time let's multiply by 1,000. Multiplying by 1,000 will move our decimal 3 times, placing it between the 5 and the 2. So that would look like 235.235 repeating. And we did it. We've got the entire repeat end to the left of the decimal. So we're happy, we're ready. That's the factor that we need to use. We're going to multiply the entire x equals repeating decimal equation by 1,000 so that we can create our second equation. So we're going to do 1,000 times x equals 1,000 times 0.235 repeating. That becomes 1,000 x is equal to 235.235 repeating. So that's the equation that we're going to use with the original one that we created. So I'm going to write the 1,000 equation first. And then I will subtract the x equation second. And I'm lining up my equations vertically so that my decimals line up on the right-hand side of the equation, because visually it makes it a little easier to see that when we do the subtraction, the repeat ends are subtracted off. So on the right-hand side, I'm left with 235. And on the left-hand side, 1,000 minus x is 999x. We want to know what x is, so we should divide our equation by 999. That leaves behind just x, so we have x equals 235 divided by 999. And we can check to see if this simplifies. You should always check to see if your fractions can be written in a simpler form. And my calculator says it cannot, so that would be our final answer. But you should also check that when you divide this on your calculator, 235 divided by 999, that you get a decimal that does look like 235 repeating. All right, let's try another repeating decimal. How about 2.345 repeating? And just to be clear, it's only the 45 that's repeating. So this number would look like 2.345454545. Just the 4 and 5 are the repeating numbers. So that makes this a little bit trickier because we need to make sure to pay attention to the actual repeated digits in this process. It'll start off exactly the same. We're going to let x be equal to the repeating decimal. And we're going to multiply this equation by factors of 10 until the repeat end appears on the left side of the decimal. The shortcut for this is to ask yourself, how many times do I need to move the decimal to the right before the entire repeat end is on the left. So I would need to move it 1, 2, 3 times. So I need to multiply by 1,000. That would give me the equation 1000x is equal to 2,345.45 repeating. Once I have that equation, I might look back and think, oh, well, every other time we've done this, we've used our first equation and our new equation together. But the problem is, and let me show you, is if I line up that 1000x equation with my x equation, the repeat end does not subtract off so nicely, even if I line up my decimals. So this won't work. We need to create another equation by multiplying powers of 10 to the original equation so that we have the repeat end matching up to the right of the decimal. So notice that 2.345, the repeat end is 1 digit away from the decimal. So I'm going to multiply by 10. So I'll have 10x is equal to 23.45 repeating. These are the two equations that we'll use against each other. I take my two equations and I align them vertically. Again, to me, that just makes it easier to see that those repeat ends will subtract off. And then I need to do the rest of the subtraction. So 5 minus 3 is 2, 4 minus 2 is 2, bring my 23 down. And then on the left-hand side, I have 1,000 minus 10, that's 990. Now I've gotten rid of all of my repeating decimals. I can solve this for x simply by dividing by 990. Leaving behind x is equal to 2,322 divided by 990. Now, these numbers, numerator and denominator, are both even. So I know that this fraction can simplify. I can factor each of these terms and reduce common factors, or I can type it into my calculator and find out that this reduces to 129 over 55. So now we know how to take a repeating decimal and rewrite it as a rational number.